All right, welcome back to another session, and this is where we'll begin to switch gears a little bit and start talking about probability theory, right? So far, what we've done, if you look back at the first three sessions, we've had a gentle introduction to statistics. Then we talked about, okay, given that we have some raw data, how do we begin to make sense of it, right? So how do we begin to chart it, visualize it, calculate some summary statistics about it, like the mean, median, and mode, figure out how much variation there is in the data set. So that in that context, we talked about the range, the variance, and the standard deviation. And then we talked about measures of position, right? So we talked about where different elements of the data set are located and what that so we can essentially fix the positional elements of the data set. And in that context, we talked about breaking the data set up into fractiles and quartiles and deciles and the box and whisker group. Okay. Now we will turn our attention to probability theory because, as I mentioned in the opening session of this course, the probability theory forms the bridge between how we go from descriptive statistics, which is basically very at a very rudimentary level, just a basic description of the data set, to inferential statistics, where we're going to use what we're seeing in the data to inform something about the state of the world, right? So the bridge between those two branches of statistics, between descriptive statistics and inferential statistics, passes through probability theory, and that's what we'll do. Okay. Uh, in this course, the treatment of probability theory is going to be at a very rudimentary level, at a very elementary level. We'll develop enough probability theory for us to make the bridge, but I just want to impress upon you the fact that what we do here as far as probability theory goes is a very, very basic introduction. There's a lot, it's a very rich subject. There's a lot of uh, amazing work which has been done in probability theory, but here we build out the base, just the essential tools that we need to make that jump from descriptive statistics to go on to inferential statistics. Okay. All right. So let's get to it. So what are we trying to do here? So we in this particular chapter, over this session and the next couple of sessions, we'll talk about some basic concepts of probability theory. Then we'll talk about conditional probability and the multiplication rule. How do we begin to operationalize the theoretical ideas of probability? Then we'll talk about the additional rule, and then we'll do a brief foray into permutations and combinations, right? So that's basically the roadmap for the next couple of sessions. All right, so let's get into it. Let's talk about some basic concepts in probability theory. And as usual, we'll begin with a few definitions, right? We need to understand what you're talking about. So let's start with a few definitions. So we'll talk about what a sample space is and how to identify the sample space of a probability experiment. We'll talk about a very um, foundational idea in probability theory. How do we count the total number of outcomes? So this notion of the fundamental counting principle, that's where we'll go next. Then we'll talk about in different contexts, how do we calculate probability? We can calculate what's known as a theoretical probability, an empirical probability, and a subjective probability. So we'll get into all of that. And then we'll see a couple of examples of how to operationalize all of these ideas. Okay. All right. So some definitions before we go any further. So the probability experiment, so when we say probability experiment, it consists of two parts of it, right? There's the probability part of it and there is the experiment part of it. So let's start with the experiment part of it. An experiment is anything that you can, any action or any task that you perform where the outcome of that task is not known ahead of time, right? So that's basically how we understand what an experiment is, right? An experiment is anything where you perform a series of actions or an action, but you don't know what the outcome of that action is ahead of time, right? You might expect a few outcomes. If you do a particular action, you might expect a range of possible outcomes, but you don't know what it is ahead of time, right? So a probability experiment is, as we understand it, is a series of experiments where we conduct the same action over and over again and record what we call the outcome, right? So when we perform this probability experiment once, the result of a single trial, every single time we perform this experiment, we're going to observe what we call an outcome. Something happens as a result of our actions, and that's what we'll call the outcome. The sample space defines the range of all possible outcomes for that probability experiment, right? So it tells us how many and what kinds of outcomes we should expect to see when we perform this probability experiment. And an event is defined as a subset of the sample space where we say an event has happened if one or more of the outcomes in the sample space appear. Okay, so okay, this is a lot of just technical definitions of what we mean by all of these things, but it becomes much clearer once we see an example. Okay, now here's an example. So suppose we consider the probability experiment of rolling a dice. Okay, now this is a probability experiment because when I roll a die, I don't know what will show up ahead of time, right? The outcome is not predetermined. That's what makes it a probability, is that I don't know ahead of time for sure. If there was no uncertainty around the outcome of the experiment, then we wouldn't have any need to take recourse to probability, right? We can just keep moving on with our lives. But once we introduce this notion of uncertainty where multiple different things could happen, then we introduce this idea of probability into this story. So this is a probability experiment in the sense that when I roll a die, I don't know ahead of time what outcome is going to show. So suppose I take a die and roll it, and a 3 rolls. So the outcome of that trial, right, when I perform this probability experiment for the first time, the outcome of that trial is a 3. Okay, a 3 shows up. So that's what we call an outcome. The sample space is going to tell me the set of all possible outcomes, right? So in this case, when I roll a 6-sided die, one of 6 numbers can show up. Either a 1 can show up, a 2 can show up, 3, 4, 5, or 6, right? So sample space essentially defines all the possible outcomes that can show up when I perform this probability experiment. An event is anything that we define, right? We say that an event has occurred. In this case, suppose the event is a die is even, right? So when do I say this event has happened, that a die is even, right? I say that the die is even when one of 3 possible outcomes show up. Either a 2, a 4, or a 6 show up when I roll a die, then I say that this event has occurred, right? So an event is a subspace, it's a subset of the sample space, because the sample space essentially defines all the possible things that could happen, and an event is said to occur if one or more outcomes of the sample space are observed. Okay. All right. Here's another example. So suppose a probability experiment consists of it's a probability experiment in 2 steps, right? First, I toss a coin, and then I roll a 6-sided die. Okay, it's a probability experiment because I don't know what will happen. I don't know in either stage. I have no certainty that this is exactly what will happen. So I toss a coin. It could come up a heads or a tails, and I don't know ahead of time whether it's going to show up a heads or a tails. Okay, when I roll a die, I know one of 6 numbers can show up, but I don't know what number will show up ahead of time. So this is a probability experiment in the sense that the outcome of the experiment is not known ahead of time. Okay. Now, suppose we want to know what is the sample space of this experiment, right? We want to know what is the set of all possible outcomes for this experiment, right? And when the situation is fairly simple, we can use what we call a tree diagram, okay? And here's what it looks like, okay? Now, this is an experiment in 2 parts. In the first part, I toss a coin. So that can show up a heads, right? This is a head, or it can show up a tail. Okay, I can get a heads or a tails on the coin toss. The second stage of the experiment, where I toss a coin, I observe what has come down, so I note it down. So if a head shows up, then I write it down as a H. If a tail shows up, I write it down as a T. Then I take my die and then I roll it, and one of 6 numbers can show up, right? one can show up. So if once I've tossed a coin and come up a heads, one of six things can happen. I could get a 1, a 2, a 3, a 4, a 5, or a 6. Similarly, once I toss a coin and it's come down tails, then one of six numbers can appear on the die which I roll next. 1, 2, 3, 4, 5, 6. So the set of all possible outcomes for this two-stage experiment where I first toss a coin and then roll a die are these uh, 12 outcomes where the coin comes up a heads and then the die roll is a 1. The coin comes up a head, the die roll is a 2. The coin comes up a tail, the die roll is a 3. So this essentially tells me all the possible things that could happen when I perform these two series of actions, right? Where I toss a coin and roll a die. And this essentially defines the sample spaces. Tells me if I perform this probability experiment, this is a set of all possible outcomes, and the total number of outcomes here is 12. So the size of the sample space is 12. Okay. All right. I hope that's clear. Again, if there's any questions at any point, just make sure that you can leave it in the comments below the video, or see me in office hours. Okay. As a small note here, it's a small definitional thing. So there's a distinction between what we call a simple event and not a simple event. A simple event is when is said to have occurred an event that consists of a single outcome, right? We say that this event has happened only if a particular outcome of that sample space, only one single outcome of that sample space is observed, then we say this event has happened. For instance, if I say, okay, my event is tossing heads and rolling a 3. Is this a simple event? How many ways are there for me to observe, say this event has happened? The only way I say this event has happened is if the outcome H3 shows up, which is to say I toss a head and roll a 3. So there's only one single outcome which satisfies the conditions of this event. So this is a simple event. Okay. Not, any event which has more than one single outcome, any event which we can say has occurred, if we observe more than one single outcome, there's many different ways this event can occur, then we call this not a simple event. For instance, the event tossing heads and rolling an even number. I would say that this event has occurred when, heads has to definitely appear. So H on the coin toss, I still need a head, but rolling an even number. So if the outcome H2 shows up and the outcome H4 shows up, or the outcome H6 shows up, right? If there's multiple different outcomes which satisfy the conditions of this event. So this is not a simple event. Okay. All right. So here's a couple of examples just to illustrate this point. Suppose you roll a six-sided die, and the event that you defined is that event B is rolling at least a 4. Okay. Now, what are the set of possible outcomes when you roll a die which satisfy the conditions that B has happened? At least in statistics and in math in general means greater than or equal to. Okay. So event B is rolling at least a 4. So if I roll a die and a 4 shows up, I know that event B has happened. If I roll a die and a 5 shows up, I can still say event B has happened. If I roll a die and a 6 shows up, I can still say event B has happened. So event B has three possible outcomes. It could be rolling a 5, rolling a 4, or rolling a 6. In either of these three cases, I would say that event B has occurred, which means that event B has more than one single outcome. It is not a simple event. Okay. All right. So when the situation is fairly, you know, uh, small and clear cut this way, we can use what we call this tree diagram to count up the sample space, to just get a visual representation of what that sample space is. It's a very useful tool just to visualize what it is that's happening in probability theory, right? If you're ever in uh, don't completely understand all the possible things that could be happening, you can just basically draw like a small version of this tree diagram just to check visually and mentally as to what the sequence of things are. Okay. But suppose we have um, more complicated situations. It's not always possible to draw these tree diagrams, and the tree diagram loses its value fairly quickly, right? If the number of outcomes and the number of stages of the experiment and the number of choices in the experiment start to grow, then the tree diagram becomes very, very cumbersome to manage, right? And to illustrate when that is the case, that's when we rely on what we call the fundamental counting principle. Okay, and the fundamental counting principle is very straightforward. It says that if there's m ways, if one event can occur in m ways and the second event can occur in n ways, then the number of ways that the two events can occur in sequence is m times n. Okay, so it can be extended to any number of events occurring in sequence. All right. So that's what we call the fundamental counting principle. So if there's m ways that event A could have happened, n ways that event B could have happened, then there is m times n ways that event A and event B happen in a sequence like that. Okay, that's what we call the fundamental counting principle. And to get to that, here's a nice little example which illustrates why this is a easier way to go about doing things rather than relying on a tree diagram every single time. All right. So suppose here's a quick example of this. So suppose you're in the market to buy a car. Okay. And straight away you can see that when you go to the market to buy a car, there's many different choices that are facing you. Suppose we limit it to these criteria, right? So you can choose one of three manufacturers, right? You could choose one of Ford, GM, or Honda. You could choose one of two sizes. You could choose a compact car or a mid-size car. And you could choose one of four colors. You could choose a white car, a red car, a black car, or a green car. Yeah. So the question then becomes, how many different types of cars can you end up with, right? A type of car is like a Ford mid-sized black. So a black mid-sized Ford car is one choice that you could end up with in this market. You could also end up with a green compact Honda, right? You could end up with all these different choices, and the question then becomes, how many different ways can you select one of how many different kinds of cars can you get out of this selection criteria, right? So if I use the tree diagram straight away, you can see it's becoming very complicated, but it's illustrative here. So my decision rests on three different levels, right? On the first level, on the first stage of it, I need to choose a manufacturer. So I can choose between Ford, GM, or Honda, and so I get these three branches of the tree. Once I've narrowed down to one of these three manufacturers, I have to choose a size. So if I choose Ford, then I have to choose either a compact or mid-size car. If I choose GM, I have to choose either a compact or a mid-size car. And if I choose Honda, then again, I have to choose again. So there's a second step here, right? Once I've decided that maybe I want a Ford compact car, then I have a color choice to be made. Once I've completed these two choices, then I could choose one of four different kinds of cars. I could choose a white car, a red car, a blue car, and a green car. Similarly, if I land on a Ford midsize, I have four different color options and so on. So if you count up all the different ways, the number of different ways in which I can end up with a car in this situation is, as you can tell, if you count up all these different outcomes here, there's 24 different ways, right? 24 different terminal branches to this tree, right? So here, the way to read this is that this G here represents a green mid-size Ford. Okay, this W here represents a white compact Honda. This B here represents a black mid-size Honda. Okay, so straight away, as you can see that if the number of choices start to begin to increase and the number of levels of the experiment begin to increase, then it becomes very, very complicated to keep drawing these tree diagrams and these branches and so on and so forth. The easier way to get around it is to just use the fundamental counting principle, right? The fundamental counting principle says that you need to do three things in sequence. You need to first choose a manufacturer. Second, you need to choose a size. And third, you need to choose a color for the car. There's three ways to choose the manufacturer. There's two ways to choose the size of the car. And there's four ways to choose a color for the car. So there's M ways to choose the manufacturer, N ways to choose the size, and P ways to choose the color. So there's M times N times P ways of choosing a car in sequence this way. And that's 24 different ways. Okay. So this is the critical idea around the fundamental counting principle, is that we can count up the number of outcomes in the sample space very quickly, right? Remember that this right here is what we call the sample space. This tells me the set of all possible outcomes for my probability experiment. Okay. All right. So one thing to note here is that we generally think about probability of in three different distinct ways. The first kind of probability is what we call classical or theoretical probability, right? So when we want to calculate a classical or a theoretical probability, what we know is that the sample space that we work with is well defined and is completely known and well defined, which is to say we know entirely the size of the sample space and all the different outcomes in the sample space, and we can count up the number of outcomes in the event E, whatever event we are considering, without any kinds of errors. Then we can calculate what we call a theoretical probability, right? For instance, if we had to find classical probabilities, suppose you roll a six-sided die and we want to find the probability of each of these events. This is a case where we can calculate theoretical probabilities completely accurately, because we know that when I roll a six, I know that the die has six sides. I know what the numbers are on each side of the die. So I know the entirety of the sample space, right? And then I can calculate what we call a theoretical probability. So event A is rolling a three, okay? If I think about event B is rolling a 7 and event C is rolling a number less than 5. So I want to calculate the probability of each of these events happening. Before I go into all of that, I need to know what the sample space is, and here I know what the sample space is. So when I roll a die, one of six possible outcomes is possible. Either a 1 can show up, a 2 can show up, a 3, a 4, or a 5 or a 6. So the size of the sample space here is 6, right? There's 6 possible outcomes that could show up when I roll a six-sided die. Okay. So consider event A, rolling a 3. How many outcomes of the sample space can satisfy the conditions of this? There's only one. If I see a 3 show up on the die roll, then I say event A has happened. Otherwise, event B has not happened. So what is the probability of rolling a 3? Out of the 6 possible outcomes, only one of them essentially satisfies the conditions of my event. So the probability of rolling a 3 is 1 over 6 or 0.167. And if you multiply this by 100%, you can also express this as in percentage terms. So there's a 16.7% probability that when I roll a die, it shows up as a 3. Okay? Consider the event B, rolling a 7. How many different outcomes in the sample space satisfy the conditions of this event? If I roll a six-sided die, there's never going to be a chance that I'm going to roll a 7, right? So there's not a single outcome in the sample space which satisfy the conditions of this event, because 7 is not in the sample space. 7 is not in the realm of possible outcomes for this probability experiment. So for event B, this is an empty set, right? There's no outcome in the sample space uh, which satisfies the conditions of the event. So what is the probability of rolling a 7 when I roll a six-sided die? It's out of the 6 possible outcomes, none of the outcomes satisfy the conditions of this event. So that's 0 or 6 or 0 or 0% chance that I ever roll a 7. And the probability of 0 essentially indicates that it's impossible that something like that could happen. Okay. Event C is rolling a number less than 5, right? Less than is strictly less, so it's not less than or equal to. So event C, if I think about event C, rolling a number less than 5, there's multiple different outcomes. It's not a simple event. This is an event which has multiple different outcomes. If a 1, 2, 3, or a 4 show up, I know I can say that event C has occurred. Okay. So what is the probability of event C happening, which is what is the probability of rolling a number less than 6, less than 5? It says that out of the 6 possible outcomes in the sample space, 4 of them satisfy the conditions of my event. So probability of this is 4 over 6 or 0.667, or this is 66.7%, right? So when the sample space is well defined and understood, then the probability of a particular event essentially is the ratio between the number of outcomes in that event over the number of outcomes in the sample space. And this is what we call a classical probability. Okay. The second type of probability that we consider is when we don't know the entirety of the sample space, where we don't know the all the possible outcomes that could occur and any of that. In that case, we collect a sample of that, of whatever it is we are studying, and use that as an approximation of the theoretical probability, right? So in general, the way we calculate empirical probabilities is to use the relative frequency of an event. Okay, so what does this mean? So suppose uh, we have a company and it's conducting a telephone survey. Okay, so far we've talked to 1,504 people. And we've asked these questions, right? What the question is, what do you think about the 2000s, right? The past decade, what do you think about it? What is your view about it? So we give them four options. They could say that they have a positive view. It could say they have a negative view. They could say that they have neither positive nor negative, or they can answer simply say, I don't know. Okay. So if I think about this story here, I've only talked to 1,504 people, right? I've surveyed only 1,504 people. So I don't know the set of all possible, answers, given that I've not surveyed the entirety of the population. All I have is a sample of the entirety of the population. So here is a case where I essentially look at the empirical probability. So given what I'm seeing inside my sample, I'll use this sample, whatever I'm seeing in the sample, to estimate. Again, be very careful with empirical probabilities. We are basically estimating the as closely as possible what we think the probability should be. It is not a precise measure as much as it is just an estimate of that measure. Okay, so uh, so what is the probability that the next person says that they have a positive overall impression? So okay, so you look at this and say, okay, the event is that their response is positive. I say that my event has happened if I pick up a phone call, pick up the phone, I call someone and ask them, what do you think about the 2000s? And they say positive, then I say my event has occurred. Okay. So now of the 1,504 people I talked to, right, of the 1,504 responses I've already recorded, 406 of them have been positive so far. So my best guess, my best approximation of what I think the probability of that next person picking, who I call, saying that they have a positive uh, view of the 2000s is about 27%. Okay, so that is my empirical probability. So as these numbers change, this probability is going to get updated as well, right? So as I talk to the next person, this probability that the person after that will say that their positive view is going to be different than prior to it. So an empirical probability is not a fixed idea. It varies based on, as the data evolves, your probability keeps getting updated as well. Okay, so that's the crucial distinction to know between these two types of probabilities that we talk about, between theoretical and empirical probability. But the holy grail here in all of statistics is uh, based on this notion of this law of large numbers. Okay, now what the law of large numbers says is that as the number of times I conduct this experiment, as the size of the sample I'm looking at keeps growing larger and larger and larger and larger, the larger that number is, the closer and closer the empirical probability will converge to the theoretical or the actual probability of the event, right? So the bigger the sample sizes, the closer I get to the truth. The more number of people I talk to, the better, more fine-grained this probability measure is, right? So for instance, if I didn't know, now we understand that everyone knows that if I toss a coin, there's a 50-50 chance, right? That's why we toss a coin to decide things where we don't want to favor one person or the other. We leave it up to chance, which is to say, if I toss a coin, half the time it's going to come up heads, half the time it's going to come up tails. That's what I mean. But that's what we know now. But suppose, we started tossing a coin. Okay, we didn't know anything about probability of the head showing up when we toss a coin. The first time you toss a coin, it either shows up a heads or a tails. Okay? Suppose it shows up a head on the first toss. what is your best estimate on what is the empirical probability? You toss the coin once, of which the number of heads that showed up was 1. So based on what you've just observed, you would say that the probability of a head when I toss a coin is just 1. And that's reasonable because that's the empirical truth that you've observed. You tossed a coin once, so that's the denominator. It showed up heads once. So the probability based of what you've observed in this world is that 100% of the time that you've done this experiment, a heads has shown up. Okay, but if you stop there, you will have a very faulty sense of the world, right? Because you know that it just gives you a very false impression because you haven't given yourself the chance to observe all the possible other outcomes that could show up, right? So if I toss a coin the second time, so suppose now I have tossed a coin twice, and on the second one a head shows up again. Now the probability of heads is still 1, right? You think that, okay, I've done this experiment twice, I tossed a coin twice, both times it showed up a head. Based of this, the probability of heads, based of this, I should believe that every time I toss a coin, it should always show up a head. I toss a coin the third time, and now a tail shows up. What is the probability of heads now? Is 2 over 3. Of the 3 times I tossed a coin, 2 of them were heads, the third one was a tail. So the probability of getting a heads was 2 over 3. This is 0.667, right? This is 67% roughly. Okay. And straight away you're beginning to refine what do you think the probability is, right? And that's the story of law of large numbers. If I keep tossing this coin over and over and over and over and over again, as the number of tosses goes up, what do you observe? That the probability of heads essentially converges and becomes very stable around this number of 0.5. It's still going to jiggle about because that's how it is, because it's an empirical probability. It's still going to move about based on what the data set looks like, but it basically converges to this true, accurate theoretical probability. And in a very basic sense, it's a very powerful idea, right? It's a very intuitive idea, and this is how we are operationalizing it in a real world situation. The more times you conduct this experiment, the higher is the likely you're improving your chances of observing all the possible outcomes for that experiment. And if you improve your chances of observing all the possible different outcomes for that experiment, you're better able to capture the sample space of that experiment. And if you have a better understanding of the sample space of the experiment, then the uh, approximation that the empirical probability is giving us is going to be very fine-tuned. It's going to be very close and starting to converge on the theoretical probability. Okay, so that's the crucial idea. All right, the last kind of probability that we can talk about is what we call subjective probability. This is basically a hunch, right? A guess, right? It's based on your intuition, but it has no empirical basis. It has no basis in data. It's not no basis. It's just a gut feeling, right? A doctor, you ask a doctor, what do you think? What do you put the percentage? What do you feel a patient chances are at making a full recovery? The doctor might just come up with a number and say, yeah, there's a 90% chance. Right? That's just a subjective, intuitive guess. It might be true, might not be true, but it's not based on any kind of underlying, empirical data set or any kind of classical or theoretical probability which was calculated, right? So this is the third kind of probability that you might encounter, this subjective probability, and it's obviously the most suspect, right? These are just numbers people are throwing out. So let's think about these three different kinds of probabilities, and we'll consider different cases and ask the question, is this a classical or a theoretical probability, an empirical probability, or um, a subjective probability, right? So the probability that you'll get the flu this year is 0.1, right? The doctor just tells you that there's a 10% chance that you might get a flu this year, probably a subjective probability, right? This is just likely an educated guess. So this is what we call a subjective probability. The probability that a voter chosen at random will be younger than 35 years old is 0.3, okay? Even before I ask you anything else, how would you go about testing whether this is true or not? Okay, you just want to goes look at a bunch of different people of the voting age, right? And you see, the more people you talk to, the better it is. Suppose you talk to 1,000 people, and of the 1,000 people, about 300 people are under the age of 35. Based on that, you could say that the probability that a voter chosen at random will be younger than 35 years old is 0.3. So this is what you would probably do, and this is what we call an empirical probability, because to know the entirety of the population and how many of them are under the age of 35 at any given point in time is kind of a virtually impossible task. You might collect a survey, a sample of the population, see what the sample of the population looks like, and use that to judge what the probability should be. So this is likely a case where we use an empirical probability. Yeah. The probability of winning 1,000 ticket raffle with one ticket is 1/1,000. This is fairly straightforward. This is a theoretical probability, right? Equally likely outcomes, there is no confusion about it. There's 1,000 different tickets, only one of them is the winning ticket. Of the 1,000 possible ticket, only one of them is a winning ticket. So this is a theoretical probability. This is completely ironclad. Okay. All right. A couple of quick notes on how to interpret the probability numbers. Firstly, when you're doing these problems, just to make sure that you're on the right track, a probability is always going to be a number between 0 and 1, right? It's never going to be any negative number. It's never going to be a number greater than 1. Because if you understand what the limits here are, a probability of 0 says that this event can never happen. A probability of 1 says that this event will always happen, right? So that's the two endpoints of for a particular event. Either an event never happens or an event always happens. So a probability of greater than 1 indicates that it doesn't really make sense, right? What does it mean for an event to have probability greater than 100% of the time? If you say probability is 1, you're saying that 100% of the time an event happens. So there doesn't make sense for probability to ever be greater than 1, because 1.42 says 142% of the time this event happens, which obviously doesn't make much sense. And always probability is always never going to be negative either, right? Because a probability of 0 indicates that the event never happens, and that's basically the lower limit, right? So the probability is always going to be a number between 0 and 1. Okay. So if the probability is 0, the event is impossible. If the probability is exactly 1, then the event is certain. And the higher the probability is, the higher the likelihood that it will happen, right? So 50-50 is 0.5 probability is even chance. This is 50-50. So if the probability is closer to 0, the less likely it is, the more unlikely it is. And the probability is closer to 1, the more likely that particular event is. Okay. All right. Last couple of things that I want to mention here very quickly is what we call complementary events. Okay. Complementary events is basically very simple. So if the box here, the rectangle here represents the sample space, it tells you all the possible things that could happen, right? The box, okay, the rectangular box. The circle here that I've here labeled here as E is all the set of all outcomes which could occur for me to say that E has happened. Okay? The complement of this event, which is written as E prime, is everything but E. So E complement, in a very simple logical sense, is not E, right? Everything in the sample space, which is the box, but which is not part of E. Everything outside of the circle is not E. Okay? So based on this, we can write these probabilities, that the probability that either E happens, right? If I look at the statement here, it says the probability that either E happens or the probability that E does not happen is equal to 1. Okay? Which is to say 100% of the time, either E will happen, which means I'll be here, or I'll observe an outcome from in the circle, or it won't happen, which means that I'll observe an outcome from outside of the circle. But 100% of the time, either I will observe E happening or I'll observe E not happening. So that's what it means. The probability of E complement plus the probability of E is equal to 1. So if I know one, I can always calculate the other. So the probability of E is 1 minus probability of E complement. Probability of E prime or E complement is 1 minus probability of E. Okay. To see this in action, here's an example that will make things clear. Okay. So you survey a sample of 1,000 employees at a company and record the age of each, right? So this is again empirical probability that you're going to calculate because all you have is sample data, and you have 1,000 employees. Find the probability of randomly choosing an employee who is not between 25 and 34 years old. Okay. So this is the category that we want to exclude. If this is E, if E is the probability that someone is between the age of 25 to 34, then we are after probability of not E. Okay. So the solution here is obviously straightforward, right? So the probability that someone will be in the age of 25 to 34, what is the probability of E here, is 366 over 1,000 or 0.366. That's the relative frequency of this category. What is the probability of someone being between the age of 25 to 34 is 366 over 1,000, 0.366. So what is the probability that someone is not, the age is not between 25 to 34 is 1 minus the probability that someone is in the age 25 to 34, right? That's what this line is telling me. The probability of not E is 1 minus the probability of E. The probability that someone is, the age is not between 25 to 34 is 1 minus the probability that the age is between 25 and 34. So that's 1 minus 366 over 1,000 or 634 or 1,000 or 0.634. Okay. Which is going to be the same, intuitively it should all make sense that it should be the same as adding up these 1, 2, 3, 4, 5 numbers and dividing by 1,000. So probability of not 25 to 34 is the probability of being 15 to 24 plus the probability of being 35 to 44 plus the probability of being 45 to 54 plus the probability of being 55 to 64 plus the probability of being 65 and over. It's going to give you the same answer. So this is just an easier way to calculate these kinds of things. So if I know the probability of an event, I can always calculate the probability of its complement of E prime or not E, right? Which is just 1 minus the probability of the event that I've defined. Right? Okay, probability using a tree diagram, just quick review of what we've done. So probability experiment consists of tossing a coin. In the first stage of the experiment, we're going to toss a coin and then spinning the spinner, right? If I spin the spinner, there's 1, 8, 2, 7, 3, 6, 4, 5. So 8 different numbers can show up on the spinner, right? Use a tree diagram to find the probability of tossing a tail, so a tail, and spinning an odd number. Okay, so let's draw the tree diagram first, and it's fairly straightforward, right? In the first stage, I toss a coin, which means that it could land a heads or a tails. So that tells me the first 2 branches of that tree. Given that I've observed what happens, so suppose the coin comes up a head, now I spin the spinner, right? So I take the spinner and spin it, then I observe what could happen. So once I toss a head, then a 1 can show up, a 2 can show up, a 3 can show up, a 4, or one of these 8 numbers. So H1, H2, all the way till H8. If the coin shows up a tail, again I do the same thing. I spin the spinner, and one of 8 different things, numbers can show up 1 through 8, right? So what is the size of the sample space? What are the total number of outcomes for this experiment? There's 16 possible outcomes. So there's 8 here, there's 8 here. So that's the size of the sample space. 16 possible outcomes to this experiment. What is my event? My event is tossing a tail and spinning an odd number. So it has to be a T. So none of these outcomes satisfy my conditions, the event, because first of all, I need to toss a tail, and then I need to spin an odd number. So 1, 3, 5, 7. These are the only 4 odd numbers. So T1, T3, T5, T7 meet the conditions. These are the outcomes in the sample space which meet the conditions of my event of tossing the tail and spinning an odd number. So out of the 16 possible outcomes, 4 outcomes satisfy the conditions of my event. So the probability of this event happening is 4 over 16 or 1 over 4 or 0.25 or 25%. Right. All right. So last example. So suppose your college identification number consists of 8 digits. Okay, so everyone has a ID card and you have an ID number, and suppose it has 8 digits. Each digit can be 0 through 9 and each digit can be repeated. Okay, what is the probability of getting your particular college ID when randomly generating 8 digits? So consider what the situation here is, right? Suppose you have an ID card and 1, 2, 3, 4, 5, 6, 7, 8. So you have an 8-digit ID card, right? So eight different digits form your ID card. And it can only be numbers, right? 0 through 9. One of those 10 digits. Remember, 0 through 9 is 10 digits because 0, 1, 2, 3, 4. Count them up. There's 10 different digits. And each of them can be repeated, right? So which is to say I can have a ID card number like 00000000, right? That is a possible ID card number, right? So if I think about the first position here, how many choices do I have here? How many different digits can I use for this position? And the answer is very straightforward, which is 10. Right? There's 10 different ways I can fill the first position. I can choose one of those 10 digits available to me, 0 through 9. I can choose one of those 10 digits. Okay, great. How many ways are there for me to fill the second position? And the answer is 10, right? Because each digit can be repeated. So when I go to fill the second position in my ID card number, it can be one of, again, 10 digits. It can be a 0, 2, 5, 9, whatever it is. Again, I have 10 choices here. So this is basically the fundamental counting principle on steroids. So if there's 10 ways to fill the first position, 10 ways to fill the second position, 10 ways to fill the third position, 10 ways to fill the fourth position, 10 ways to fill the fifth, sixth, seventh, eighth, then there's 10 raised to 8 number of ways to fill all these 8 positions with these 10 digits which are available to me where repetition is allowed. Okay. Only one of these numbers, however, is your college ID number, right? So what is the probability of you getting your ID number is all the possible ID numbers that can be generated using the scheme, only one of them is your ID number. So your probability of you getting your particular card number is 1 over 10 raised to 8. Right? It's a very small probability. All right. So that's where I'll stop this session. So this is again introduction into probability theory. In the second session, we'll go on and talk about conditional probability and the multiplication rule. But that's starting to employ what we've already developed here. But it should, probability in its fundamental sense is a very intuitive concept. So, for the most part, you should be able to figure out if a probability doesn't make sense by just doing a sanity check, right? So it's a very logical way of thinking about uncertainty. And once we introduce this notion about thinking about uncertainty into the mix, then we can step into talking about inferential statistics, which is where we are going in a couple of weeks. All right. So again, if there's any questions on any of this material, please let me know, and I'm always happy to help. Thanks for listening, and I'll see you in the next one. Bye bye.